SPC, can help to control process and ensure consistent output to deliver products that will meet customer requirements and result in customer satisfaction. SPC is an effective method to drive continuous improvement. A process is capable if the outputs produced are within specification limit. A process is stable if it is only influenced by common cause of variation. SPC is the 11th element named Initial Process Studies in 18th element of PPAP. Goals of SPC: help the process operator to find and eliminate special cause variation, reduce common cause variation and maintain a process well in statistical control with high process capability. Advantages of capable process: consistent outputs. A capable process with a low level of spread will produce consistent outputs. Cost savings: in process and final inspection can be reduced, resulting in lead time and cost savings. Defect rates will be low or may even be eliminated. There will be low levels of scrap, rework, repair associated with a capable process. Commonly used control charts for variable subgroup data are the X bar and R charts and X bar and S charts. Variation in the process occur in two major ways: the range changes and the mean changes. X bar chart monitors the mean of the process while the R and S chart monitor process variability. X bar chart representation of variation among the average of subgroups. R bar chart looks at variability within these subgroups. When the range chart is in out of control status, the rules for evaluating X bar chart should not be used. Common and special causes. Every process has variation which is divided into two categories: special and common. When a process is stable, it only experiences common cause variation that is normal and inherent in the process. Special causes in a process result in instability over time and inability to predict the output. Common cause variability is expected, natural, usual, and inherent in the design of the process. It affects every product. It will not be detected, controlled by process operators. Variation falls within control limits of control chart. Example: variation in raw materials, poor working conditions, slight vibration in machine, air pressure, ambient temperature, and humidity measurement system. Common cause variability can be reduced by redesigning the process. Special cause variation fall outside of control limit. When detected, can usually be removed or adjusted. Does not affect every part. Example: tool wear, improper setting in machine, no preventive maintenance, no training, change of operators and broken equipment. Special cause of variance can usually be eliminated with adjustment to the process, components or methods. When to use PPPPK, CP and CPK. PP and PPK uses complete set of data for calculating performance of the system. Samples taken from one shift one day's production, one shift production. CP and CPK uses samples within batch subgroups for calculating the process. Difference between specification limit and control limit. Specification limits are based on the product design. Customers set the limit on the product parts characteristics. Voice of the customer is the input for customer specification limits. Control limits are calculated variation from the process data when the process is in statistical control, so it is called voice of process. Control limits are located 3 sigma away from the average or central line of the chart. Control limit is divided into 3 equal parts of 1 sigma each. These are called 3 sigma limits or sigma zones. 68, 95, 99.7 rule for normal distribution says that as long as the process remains in control, we can expect 99.73% of the values of X will fall between 3 sigma control limits. Preliminary process capability. Preliminary process capability studies or short-term studies. Studies conducted to obtain clear information on the performance of new or revised process. Example: study conducted at the time of paper, at the time of new product development process change. Sample size at least 125 pods should be taken over a short period and measured. Short-term study is based on the data collected for a short period. Same operator load, same load tool and setting in a shift in a day. PP. Calculating preliminary process capability ratio. PP tells whether or not the production process is capable of making the parts within specifications. PP equal to tolerance divided by process variation equal to USL minus LSL divided by success, standard deviation of total population. This study is for entire population. PPP taken into account between subgroup variation. Here standard deviation, overall variability. Accounts for both common cause variability and special cause variability. PPK. PPK alone does not indicate if you are producing within specification but also indicate whether the process is centered between the specification limits or not. PPK is a measurement of how close the center is to either the upper spec or the lower spec. PPK equal to smallest distance to the tolerance limit divided by half of process spread. Let me see CP, current process capability. Current process capability studies are long-term studies conducted after bringing running process under statistical control. That is, when all special causes have been eliminated. Applied during mass production to forecast potential process capability. Sample size is the number of parts checked in each subgroup, remain constant in all subgroups. Sample size for SPC equal to 100 samples, 20 subgroup of 5 parts. Example, at least 100 parts must be sampled over the entire lot. Number of subgroups equal to 10 or 20. Each subgroup would consist of 4 to 5 consecutively produced parts under the similar process condition. Single tool, single die. Minimize within subgroup variation of samples by rational subgroup method. Collect 4 parts, skip 4 parts. Similar. Consecutive units taken in a row would be the best way to achieve minimum sample variation. As in the image. Any variation within the sample should include the normal inherent process variation. Subgroup frequency, timing between subgroups, maybe 4 parts for every hour. Define the frequency with aim to detect process changes over time. Such potential cause of changes could be due to work shift difference, relief operators, warm-up time, change in material or change in machine setting. CP calculation. CP determines only the spread and not the shift in process. CP tells if your process is capable of making parts within specifications. CP equal to tolerance by process variation. This study is for entire population. CP takes in account within subgroup variation. Sigma inherent variability only due to common cause of stable process. Calculation of CPK is a measure of how process is centered between the tolerance states. CPK determines both the spread and shift in the process. CPK should not be calculated unless the process is in a state of statistical control, because the estimate of sigma used in calculation will be unreliable. CPK equal to smallest distance to the tolerance limit by the half of the process spread. Current process capability, preliminary process capability. The minimum required for process capability is 1.33. In other words, the process spread has to be below 75% of tolerance used. Below image will give you clear idea. Impact of CPK on production. If CP equal to CPK means the process is correctly centered. If CPK equal to greater than 1 means highest PPK means that the process will need to inspect less frequently, allowing for more machine uptime and faster production turnaround. Interpreter of process capability index. CPK equal to CP means process is capable continuous process rather running closer to or near to target. If CP is not equal to CPK, process is potentially capable. If both is not equal, process is not capable. Collecting data, our measurement must follow the rules below. Gauge resolution. Gauge should be calibrated and gauge resolution should be at least 1 by 10th of the specification. Production order. What should be measured and recorded in production order? Record all data that was as well as was that file. Ensure traceability. Make sure all measurements are traceable back to 5Ms only. Record unit number or serial number for each part. Homogeneous data. A change in one of the 5M1E values may result in non-homogeneous data. For example, do not use two different types of equipment into a single data set. Creating on chart. Collect initial set of samples. Homogeneous data. Gauge resolution and traceability to cut all data. Calculate mean of such subgroup. Calculate range for each subgroup. Calculate the average of the X bar. Calculate the R bar average of R values. Calculate control limits. Calculate R chart. Based on subgroups, select the appropriate constant called default. Plot the data on the R chart. If no subgroup goes out of control limits, then accept the range as forming a homogeneous group. For the X bar chart, limit used, draw a solid line at the X bar or main. Draw lines at 1 sigma based on below calculation. Draw warning lines 2 sigma based on below calculation. Draw action line 3 sigma based on below calculation. Alternatively also you can use similar below formulas. Plot the data on X bar chart. After constructing the control chart, follow the below rules to assess stability. Rules for determining statistical control. The following rules can be used to properly interpret control charts. Rule 1, any point beyond the 3 sigma control limit. Rule 2, 8 or more consecutive points on one side without crossing mean. Rule 3, 6 points or more in a row steadily increasing or decreasing. Rule 4, 14 points in a row alternating up and down. Rule 5, 2 out of 3 consecutive points fall above 2 sigma. Rule 6, 4 out of 5 consecutive points are falls above 1 sigma from the mean. Rule 7, 15 consecutive points are within 1s of the center line. Rule 8, 8 consecutive points are falls above 1 sigma from the center line. Below images interpret clearly for you all. When we see special cost variation, take the following steps. Investigate what caused it. Was it due to internal, like change in fraud process, or any external factors? Determine is any action is needed. The control limit or plotted was miscalculated if appropriate. Implementing SPC. Select critical to quality product characteristics identified by CFT during design failure mode effective analysis. Select critical process. Means if something goes wrong with that process, it will probably have a big impact on at least one CTQ. Critical process indicated with stop on the control plan. Gather data and process knowledge of what impacts the output of the process. For example, the variable that might affect the output of a gluing process are listed below. Process input glue, process settings, cycle time, fixture, environment temperature, humidity, etc. Control independent variables that have a sizable impact on the process output. Gather data on the variables you identified previously on a regular basis. Example 5 random samples every 4 hours. Plot them on a chart. Look for ways to reduce variation. A special cause of variation may be obvious or it may take months of investigation to find it. Keep it up in the long term. Set a new target and keep controlling the key variables. Establish a plan for continual process improvement. Once a stable process state has been attained, steps should be taken to maintain it and improve. Means the process average should be centered or narrowing of the plus or minus 3 sigma limits.